Right, everyone, if you want to quieten down now, because we are going to talk today more about sea ice. And in particular, we're going to talk about the importance of sea ice, both to the Earth system, but also to the ecosystems. So today is Polar Bear Day, and I'm sure you're very excited about that. First of all, does anyone know what my image is on the front? It's not a familiar looking image, is it? It's a very rare image indeed. It's actually taken of that sort of where those lines converge in the top corner there. That is the North Pole. So we are looking at a satellite image, and it's relatively cloud-free for once. And you can see the sea ice that extends across that area, and you can see the leads and how that sea ice is partly broken up in some places. Okay, so let's move on. So today, oh, hang on, I haven't started the silly software. Give me 1 minute. That would help. Okay, that should work now. Right. So, before we get started, I want to know what you think, because there is no point you telling me if you do or you don't like something at the end. Well, you can tell me you do like things at the end of the class as well, but there's no point you telling me you don't like something at the end of the class, because that really gives me no time to change things. So if there is something that I could do differently to help you learn, that the TAs could do differently to help you learn, then now is the time to let us know. And I am pretty responsive to these things, and at least if I don't change something, I'll usually tell you why I'm not going to change it. So that can help clarify things as well. So I really would appreciate it if you could spend a couple of minutes, if you have some things to say, filling out the midterm evaluation. It's open until midnight on Sunday, so if you're going online to take the quiz, you could quickly fill it out. So things like, are the recordings helpful? Are the readings helpful? Would you like more information that I haven't provided? Are the quizzes helpful? And particularly, are discussions useful? Because it's the first time I've tried this for this class where instead of taking home homeworks, you have those worksheets in discussion time, which gives you a chance to practice the math with the TAs and with other people, and hopefully also debate some issues. I've heard there's been some good debates going on. So are those helpful? Are they interesting? Do they keep you up to date? So those things I would love to hear from you if you have comments for me, please. So on to today. So we're going to split today into two parts. Firstly, we're going to talk about the importance of sea ice to the Earth system, the much broader Earth system, in particular our climate system. But then we're also going to introduce this idea of sea ice as a component of our polar ecosystems, both in the Arctic but also in the Antarctic to a certain extent. And so there we're going to have to introduce some of the terminology that we use in Earth system science. And it's mostly stuff you might have heard of from school, things like food chains, food webs, and how energy cycles through an ecosystem. And then we'll look at the specific components of the ecosystems, including our polar bears, and why they are so special and why these ecosystems are so fragile. And then Friday, we're going to really focus on what we've been observing in terms of the trends in sea ice, and really what those implications are going to be for our very charismatic creatures of the Arctic, and also for us as well in terms of economics and transport. So, first off, it's been a long time since we've talked about albedo, and I know how much you miss it. So here is a lovely little graph showing the albedo of a whole bunch of different surfaces related specifically to sea ice. Because remember, when sea ice forms, we now have a nice solid layer. It doesn't just stay sea ice. We now have a surface that we can pile on snow and things if we want to. And that often happens in the Arctic. So you can see that when we have lovely dry snow, it has a very, very high albedo. And then we go into wet snow, sort of bare ice. And by the time we get into things like our melt ponds, so the new melt ponds and then the deeper ones and then open ocean, we're getting right down into much lower albedo values again. So you know what's coming next. I have a little feedback loop for you because it's worth remembering these. It's going to be a running theme of the class. So take a couple of minutes, think about it. think about which arrows, which notation you would use to connect these together. Okay? And don't fall for my obvious trick. Okay, so let's think about this. Oh, I should have put temperature rather than increased temperature. But in any case, if I increase my temperature, what am I going to affect? What am I going to first affect? The amount of sea ice. Okay, so I'm trying to break you out of this habit that feedback loops always go in one direction, in clockwise, okay? It doesn't have to, it's just the way that we happen to have drawn it so far. So remember that we're not just drawing things in a loop, we're looking for causality. So I'm going to increase my temperatures. What is that going to do? Yes, it's going to change albedo, but why? Okay, so we actually, this time we're going to go the other way around. Okay, going to go counterclockwise. So if I increase my temperature, I decrease the amount of sea ice I have. So what sort of arrow do I want? One with a circle at the end, absolutely. If I decrease the amount of sea ice, what do I do to albedo? Decrease. So what sort of arrow do I want? The regular, right? Yep, regular arrow. If I decrease the amount of sunlight, what am I going to do? Oh, sorry. If I decrease the albedo, what am I going to do to temperatures? Increase. So what sort of arrow am I going to have? The circle one. Yep, absolutely. Okay. So hopefully in your notes you have something that looks like that. And I always want you to remember that just because we've drawn them clockwise, because that's logically sort of the way it makes sense in my mind at least, doesn't mean that it always has to be that way. Remember, you're looking for something causing a change in something else. Okay? Great. So the other thing that sea ice does, so we have this sea ice and it creates this amazing white surface at the top of our planet, which reflects back a lot of energy. And so if we're going to lose that, we're concerned about how much extra temperature rise we might see in the Arctic. And really, that's the effect that we're seeing today that's causing our temperatures to rise much more quickly there, and will continue in the future. But the other thing that sea ice does is that we sometimes don't necessarily think about it, is that it forms a lid. It forms a barrier, basically, between our ocean and our atmosphere. And that's pretty important because, especially in these really cold regions, especially around winter time, then our ocean, even though it's pretty damn cold, you wouldn't want to go swimming in it, it still has a lot of heat. It can still release that heat to the atmosphere. That air is going to be colder than the ocean, and so there would be exchange of heat going on. Not only that, but we're sort of putting a lid over this source of water vapor. So we've said that the Arctic is a really dry place, which is funny because it's an ocean. But actually that air is so cold that first of all we can't contain much water vapor in that air. But also if we have this covering of sea ice, it's pretty difficult to get evaporation going on as well. We can get sun sublimation from the ice, but still. And so you can really see this, I think, beautifully when you open up a little space in that sea ice, when you expose the ocean to the atmosphere. And you can see it's not because the ocean is hot here. It's not bubbling like your hot tub sort of steams. It's steaming just because even though the ocean is cold, the atmosphere is way colder. And so we are getting exchange of energy and also gas, that sort of water vapor you can see coming off there. And so the fact that we have this barrier there does have an effect on our weather systems, for example, in this region. And so you can see at the top here, that sort of map shows storm tracks between 1950 and 1972. And then you can see the storm tracks now between 2000 and 2006. And yes, there are some other things going on, but you can see that there's been a huge increase in the storm activity in the Arctic area. And this also has another sort of feedback loop on the fact that if we have big storms coming through, that might make our sea ice more likely to break apart as well. So all of these things come back. They all have an effect on each other. And lastly, we're going to spend a little time talking about this, seawater density. So do you remember my brinacle, the icy finger of death that destroyed all of those poor little starfish on Monday? And we saw that as that salty brine, as that really salty cold water came out of underneath the ice, it sank, right? We got this sort of brinicle come down and then it sort of spread along the sea floor. And that's because that water is really dense. So seawater density depends both on its temperature and also on the salinity, okay? And so if you have hot water, then all of your molecules are fairly spread out. They have lots of energy, they're occupying a larger space, so it's pretty low density. If you don't have much salt, if you've got fresh water, that's also pretty low density. But as we add salinity, we just basically add mass to the same amount of water, okay? So hot, fresh water is less dense. Cold, salty water is more dense. And so what we do is, as I'm sure all of you are way too young to drink and would never do such a thing, but hopefully you've seen the layered cocktails people make, and you can pour in different layers and it forms sort of funny layers. And it's the same sort of thing if you pour sort of water over honey. Then you don't get honey on top and water underneath, do you? You get water on top, honey underneath, because there's a density difference. And so you get what we call stratification, or basically just a fancy word for being layered, okay? And so what would you predict about the water at the bottom of our oceans? What would you predict about the water at the bottom of our oceans? If anyone's at the back and wants to come, there's some seats at the front. So it doesn't look that comfortable back there. Okay, have we got most votes? Right, let's take a look and see how we do. First question of the day. Pretty good. I'm impressed. Good, absolutely. So if cold and salty water is the densest water, it's going to be at the bottom. So just like honey is the densest of my liquids, it's going to be at the bottom. Okay? So you're right that if we went to the bottom of the ocean and sort of pulled up some water from down there, it would be pretty cold and pretty salty. Okay. What would you predict about the water at the top? Warmer and fresher. Absolutely. Good. We've got the idea. So this is what it would look like if we drew little graphs and everyone's like, oh, it's a graph. If you can understand that it's cold and salty at the bottom and it's sort of warmer and slightly fresher at the surface, you can do this. Everyone in my oceanography class freaked out in the midterm about this. And it's fine, honestly. It's a graph, but it's not that terrifying. So you can see that on my left-hand side here, I've got temperature. And I'm going from colder on the left-hand side to warmer on the right. And I'm going from the surface at 0 meters to 4,000 meters depth. So the oceans are really deep, so 4 kilometers down. And so you can see that further down in my oceans, it's colder, which is basically what you predict. And then as you get towards the surface, it gets warmer. Why does it get warmer close to the surface? Yeah, it's the sun. We're getting radiation from the sun and it's heating it, okay? And so that's sort of what the left-hand side shows. And there's, so one of the funny tricks about the ocean is that really it's pretty much the same, like from maybe 500 meters, 1,000 meters down. Most of it's pretty boring. It's pretty much the same sort of temperature, the same sort of salinity. It's really only in that top 1,000 meters or so that it gets sort of vaguely interesting. And so you can see that that sort of shaded orange area there marks a point where it goes from being pretty boring and cold consistently to much warmer in the surface. And we call that area where we see a really sharp change in temperature as you sort of change your depth. It's called the thermocline. And then in our sort of right-hand side, we can see salinity. And we're going from 32, which is sort of pretty low salinity, up to 35 or so, which is pretty average ocean salinity. And you can see, just like you predicted, it's saltier in the deep ocean. And it doesn't really change until you get really close to the surface again. And do you remember we talked about all of those different ways that we can change salinity? We can add water from rivers or ice, from rainfall. We can evaporate sort of material. And so those things are happening, but again, very much in the surface. Okay? So really our salinity goes pretty constantly up, and then there's a point called the halocline, a range of depths where that salinity changes really fast up to the surface. Does that make sense? Yep, good. So, the density differences that we see there between the surface ocean and the deep ocean, and if you think about it, probably in different parts of the surface ocean, so we have some colder parts, some hotter parts, some saltier parts, some fresher parts. All of those density differences means that our oceans are circulating, okay? Just like if you poured water and honey together, they would separate out. They're circulating, and we call that circulation, this really deep, slow circulation, thermohaline. The clue is in the name, thermo, temperature, haline, salt, okay? So it's driven by that density, that temperature and salinity differences. And so coldest and saltiest water is the most dense. And so if we want to start sort of sinking water to start our circulation, we need it to be cold and salty. And so this is our big thermohaline circulation. Has anyone seen this before? Only a couple of people. Okay. In that case, it's somewhat new. But the dark blue there represents deep ocean currents. So things that are basically the flow of water at the bottom of our oceans. That paler sort of whitish color shows surface currents. So you have to think in 3D here. And what you can see is that it's all connected. It's just like a conveyor belt. So if I pull on one bit, the rest of it is going to move. And so what you can see is that, especially up in the Atlantic Ocean, remember the Atlantic is the one between North America and Europe, as we get up to sort of that cold places around Iceland, Greenland, then up there it's so cold and it's so salty that actually that water can sink right down into the deepest part of the Atlantic. And then it flows down through the Atlantic, all the way along the bottom of the Atlantic, then it flows sideways and up into the Indian Ocean, and further along up into the Pacific. And then in the Indian Ocean and the Pacific Ocean, it sort of gradually makes its way up to the surface again, as it sort of mixes in with the overlying water, and then that sort of warmer white current flows back along. And I have a little video because it can be difficult to imagine, I think, what's happening here. So it's going to do some funny zooms in a second, which will help you to sort of see it. So you can see that we've got red representing warmer surface currents, purple where it's sort of coming up to the surface, and that blue is the deep part of the circulation, okay? So that blue is really what's flowing along the bottom of our oceans, and then it sort of comes back up in that Indian Ocean and Pacific Ocean to the surface, and it flows back around, okay? Does anyone know how long it takes on average for a water molecule to complete that loop? Anyone want to guess? No? Everyone's feeling too shy today. Probably something like 1,200, 1,500 years. So it's pretty long. It takes a really long time. It's very slow. But it's pretty important for our sort of system that this happens because it does move enormous amounts of heat around. Not only that, but that deep water stores a lot of stuff. It stores nutrients. It stores a lot of carbon. And that's what we're mainly interested in today, the fact that we have this deep water that's full of carbon dioxide from our atmosphere in the North Atlantic, and it's sinking down into the deep ocean, and it's going to help us out because it's going to store some extra carbon, but eventually that carbon is going to pop up again, okay? But not for 1,000 years or so. So this is a really important system, okay? And so how could sea ice formation help us with that first point? So up in the North Atlantic there, okay? How could sea ice formation help us with that first initial sinking? What happens during sea ice formation to the water? It gets salty, absolutely. So it's already really cold. But actually it's somewhat fresher, do you remember, in the polar regions? But if we can form sea ice in our winter when it's really cold, we can also make that water really salty. And now it's cold and salty enough that we can get it sinking into the deep ocean, okay? And that's why salinity is so important, okay? Temperature affects density much more than anything else, but if we add in the effect of salinity, then we can get the sort of deep water forming. And so, this is a familiar idea to those of you that have seen The Day After Tomorrow, but you may not have realized it at the time, okay? because it's really what they're talking about. There's a line in there that you probably didn't notice, but it's like, we've hit a critical desalinization point. Exactly. So, and they did. And so we're going to come back to this idea properly. We're going to spend a much bigger chunk of a lecture on it. But the idea is that today, if we're not going to have as much sea ice formation, if we're getting fresh water coming off Greenland, then we're concerned about how much deep water we're going to form and how that is going to change the sort of much, much bigger scale ocean circulation. It's pretty difficult to measure circulation on a whole ocean scale. So there are really interesting questions there. So we'll come back to this question further on in the class. So now let's talk about our polar ecosystems, the ones that are so dependent on the fact that we have this amazing sea ice around. And there's certain things about polar ecosystems, okay? The plants and the animals we see in these regions, we don't see a huge amount of diversity. Does anyone know where the most diverse places are on Earth? The rainforest, absolutely. And we have really sort of nice conditions there. It's always hot, it's always pretty sort of wet, and so there's a lot of diversity there. But as we go into polar regions, we see these huge changes in seasonal temperatures. They have to be really very well adapted to those conditions, and so we get a lot less diversity. We get less numbers of different species of plants and animals. But they are these really amazingly specialized, and they have adapted to this cold, and so they can outcompete. In these particular environments, they can outcompete sort of animals that are in the warmer conditions. And so what that means is that these ecosystems are really fragile. And so we're going to talk on Friday about how the fact that they are dependent on the sea ice means that if it's removed, they have to sort of dramatically change their way of life, and how they might not be so efficient at outcompeting things sort of from the Pacific and the Atlantic, for example. And so they care about changes in the sea ice extent, the thickness, and the timing of its formation and melting. And obviously we're going to see year-to-year changes in that, but the changes that we're seeing, say, in the past few decades have very much sort of outstripped that normal variability. So, quick question for you. If you know the answer, don't give the game away. Where would you find polar bears and penguins in the same ecosystem? And I'm talking about real world, not Coca-Cola ads or anything like that. Or Disney. Any more? Last few seconds? Okay, let's take a look. See how good your natural knowledge is. So 51% of the class is right. Okay, you don't ever get polar bears and penguins in the same place, apart from in zoos and on adverts and things, okay? The word Arctic means bear, so Antarctic is without bears. So we don't get penguins in the Arctic, and we don't get polar bears in the Antarctic, okay? They're entirely different places and different ecosystems, okay? So, on to slightly less glamorous stuff briefly. So really, if we're going to talk about food chains, ecosystems, then really the most important thing about our ecosystems is really that photosynthetic stuff at the beginning. That's really by far the most important thing. Without that, then we don't have the rest of our food chain. And so we want to think about how organisms acquire energy. And so we have autotrophs to begin with. So autotrophs is basically like self-feeding. And so these are capable of making organic molecules using energy from the sun. And in that case, we call them photoautotrophs. Photo means light. Or from chemical reactions. And that's not so important for what we're going to do. But does anyone know of a purely chemoautotroph sort of ecosystem? Who's in my oceanography class? You should know. I heard someone mutter it. Yeah.
The vents on the bottom of the ocean.
Absolutely, the hydrothermal vents at the bottom of the ocean. If you haven't ever heard of them, don't know what they are, look them up, they're really cool. And so those ecosystems are entirely disconnected from the sun. But really, for our purposes, we're really just talking about photoautotrophs in the Arctic and Antarctic. Okay? And really, it's that familiar reaction, which is CO2 plus H2O plus energy from the sun, goes to CH2O, which is just sort of simple glucose, plus oxygen. And what's that reaction called? Photosynthesis. Okay. So heterotrophs, these are sort of feed on other things in order to get their energy. So they use organic compounds from other things and decompose them in order to produce energy. Okay? So here we have our CH2O, our glucose again, and we're combining it with oxygen to make energy and water and CO2. What's that equation called? Respiration. Which one of these are we? Heterotrophs, absolutely. We don't photosynthesize. We don't make our own energy. It would be much easier if it did. Okay? So these are our sort of two types, and our autotrophs are really the base of our food chain. So this is sort of what happens with our simple food chain. This isn't an Arctic example, but it gives you the idea. So we have energy arriving from the sun. We have our photoautotrophs that can make use of that energy and create organic molecules. And then things like our mice, our snakes, our hawks, and then lastly our fungi, our worms, our decomposers can make use of those initial organic molecules created in order to generate their own energy. Okay? So energy moves from one to another throughout that food chain, and lastly it gets returned to the environment. Okay? So familiar enough idea. In reality, we don't get food chains. We get splodges, okay? We get food webs, because things aren't that picky about what they eat often. And so instead of just sort of simple linear chains, we get something that looks much more like this. This is sort of one from the Pacific, okay? So we use sort of food webs instead, and that's a much more accurate way of describing what's going on. Okay. So we have certain terminology that we use to describe what's going on. And in particular, we talk about trophic levels. So our photoautotrophs are our first trophic level. They're also what we call the primary producers. Okay? They're the primary producers. Our little mice here are our second trophic level. They're our primary consumers. Okay? They are the first consumers in the chain. Then we have our snakes. These would be our third trophic level, and they would be our secondary consumers. Okay? And then so on, our hawk would be fourth trophic level, etc. And then these last things like the fungi, worms, these are our decomposers, bacteria. Okay? Does that sound familiar? Hopefully? Okay. So I have a little theoretical sort of thought experiment for you. So here I have my very healthy looking frog. I have a little mosquito that comes along and it bites the frog and it gains energy and then it flies around and the frog will eat it. Does the frog get equal amounts of energy from eating the mosquito as the mosquito got from sort of taking blood from the frog? No. Why? Absolutely, it's using energy, right? It's flying, okay? So even though it took a certain amount of energy from that frog, as it flies, as it moves, it's producing heat energy. And that heat energy doesn't get contained in a nice form that's reusable, it just dissipates into the environment, okay? So this is why my little perpetual motion thing doesn't work. And it comes back to those laws of thermodynamics that we did way back now in first week, which I'm sure is sort of dimming into memory. And that's the idea that energy can't be continuously recycled within an ecosystem. So our first law still stands, that energy can't be created or destroyed, but it can be transferred into a less useful form. So for example, as that mosquito eats or consumes that blood, then it's breaking down that sort of chemical stored energy into sort of kinetic energy, and some of it goes into heat energy as it moves. Okay? And so that's true of all of our steps. You can see that at each of these steps, heat is lost. Just as our mouse runs around, it's using up some of that energy escapes into the environment. And so at each step in our food chain, we're going to have less and less energy available. And this sounds familiar, but it may not be something that you've necessarily thought of before, that we have more grass than we have grasshoppers, we have more grasshoppers than we have sort of toads, we have more toads than we have snakes. And it's not just because the animal gets bigger each time. But sometimes that's a sort of a misconception that we have. It's not just because snakes are bigger and so there can't be as many of them. If you add up the total weight of snakes versus the total weight of the grass at the bottom, then there's actually much greater weight of grass than there is in our snakes. And that's really because of that fact that we're not perfectly efficiently passing that energy from one to another. We're losing some of it to heat energy, and also just not all of our grass gets consumed. If our snake eats our grasshopper or our mouse, it doesn't perfectly sort of use all of it. And so energy is wasted at each step, and so each step up the trophic level, you can support less and less biomass. You can support less and less of the same creatures. So let's look at some of our polar ecosystems. Which pole am I at, north or south here? North. What gave you the clue? The polar bear. Okay. So you can see that we start off with our little sort of phytoplankton, so little floating photosynthesizing organisms, and then they go on through this food chain into our whales, into our sort of more photogenic creatures here. According to my diagram, what is the highest possible trophic level of my polar bear? What is the maximum number of steps it takes to get up there? Any last answers? Right, let's take a look, see how many people can count. Most people can count, but not all of them. Okay, so D is the right answer. It's 5, okay? So let's have a look at which our 5 stages are. So 4 is a possibility, but if we're looking for the maximum, you can see our little phytoplankton get eaten by our little copepods, little swimming creatures. They can get eaten by our little amphipods, which can be eaten by our cod. So at 1, 2, 3, can be eaten by our harp seal, can be eaten by our polar bear. So it can be 5 steps. So really our polar bears are very high on the trophic level, whereas things that we might expect to be high on our trophic levels, like our humpback whales, for example, they're actually eating these really tiny creatures. So to a certain extent, some of the primary producers themselves, but also some of these primary consumers. And so these things need to eat enormous numbers of these things in order to function. But our polar bears, our seals are more specialized. What about this one? Where am I now? Yeah, we're in the Antarctic. Okay, what made you spot the Antarctic? Penguins, absolutely, very cute little penguins. The other thing that I want to point out to you, which is really cool, if you haven't seen it, you should go look it up, are leopard seals. These things are vicious. We think of seals as being cute, cuddly, they lie on the ice, and are very photogenic. Leopard seals are pretty mean. They're like sort of big predator of the Antarctic, and they have taken out people, some of the scientists that go down to Antarctica. And so if you ever are a diver in Antarctica, they ask you to say, oh, do you have any tattoos? Because sometimes they don't bind all of you. And so there's a really cool video I found of someone that's was for National Geographic, was filming the penguins jumping out of the ice, and he was sort of lunged at by one of these leopard seals. It's a really interesting little 20-minute talk. I'll post it on the Facebook page. Okay. So let's have a look at some of those things that are common to a lot of our ecosystems. So first of all, we have our primary producers. These are our phytoplankton, our photosynthesizing algae and bacteria. And we do have specialized ice algae. So algae that doesn't just live floating in the ocean, but actually lives within the sea ice itself, which is pretty neat. And you can see some of it there, sort of in the ice. And so when do you think, this also shows this sort of layer of like red-looking stuff is actually, it's a sea ice core, and you can see all of that bacteria and algae in the bottom of that sea ice. When do you think the most primary production will occur? What do we need for this, for primary production? Yeah. Sunlight. Is this a problem in the Arctic and the Antarctic? Sometimes, yeah, absolutely. So in the winter, we're not going to get enormous amounts of primary productivity. Because remember, in large parts of the Arctic, we have 24-hour nights for the winter at least. Whereas in the summer, and especially as that spring gets going, we can have massive sort of blooms of plankton because they've basically got all sunlight all the time. Okay? So our most primary productivity is at certain times. It's spring, summer, and when sunlight can provide that energy, and also when some of that ice melting can provide some nutrients to the system. So you can see this is a very simplified diagram, but it basically shows that, remember that little photo I showed you of all those little brine channels? These little brine channels form environments where we can have little worms, little crustaceans, little algae and bacteria that can live in there. And they're pretty specially adapted because remember, it's really highly saline. It's really salty in those little brine channels. So these things are very specific to sea ice environments. And then our primary consumers, what is going to be eating all of our nice sort of green algae? We have things like annelids, so there's just big words, but basically they mean things like worms, copepods, which is sort of what you can see on the left, krill, if you've heard of krill, it's what feeds a lot of our big whales. This is sort of a swarm of krill, and they're sort of like this big. So they're really tiny, and you have to eat a lot of them if you're a huge whale, okay? And so these are what we call sort of zooplankton. So they float, and they sort of within the surface ocean. And they're often either within those brine channels or just underneath the sea ice, because that's where their food is likely to be located, okay? And then our secondary consumers, we have our whales, we have our penguins, we have different types of fish. We have a lot of Arctic fish that are very specific to our Arctic Ocean, okay? And now we have our higher trophic levels, which of course are our fun seals, our sort of higher order fish. We have our polar bear, which is having fun, and we have walrus, which is one of my favorite things, okay? So all of these things, as well as seabirds, form our sort of tertiary consumers and the top of our food chains and food webs in these areas. So let's think about some of the adaptations that these sort of top level, because basically I know everyone's interested in this stuff rather than the krill. So let's think about some of the adaptations that they have. So a lot of seabirds, you can see that their color is specific to sort of ice and cold environments. And a lot of them require sea ice. Emperor penguins, they have their breeding cycle. They form those big colonies on sea ice. And we're concerned about what might happen in the Antarctic if those big sort of areas of sea ice disappear. And it could be that they'll be fine, that they'll find areas on land, but we just don't know how adaptable they're going to be yet. So it's an interesting question. Our seals and our walruses, especially some of our seals, are really extremely adapted to sea ice environments, especially our little ringed seal. And there you can see in my top left picture, it's a little ringed seal watching us. And this sort of diagram shows how ringed seals use that sea ice. They form these little breathing holes, and they actually build snow dens on the sea ice, and they have their pups in winter within those sea dens, those sort of dens on the ice and those snow. And those sort of pups are pretty white in color to camouflage themselves, but they're not that hardy. And so especially as we get earlier snow melt as well as sort of sea ice retreat, then these things can have to sort of end up in the water a lot earlier than they should. And also things like the den collapse can affect them. Our walrus also sort of rely on the sea ice as somewhere to pull out as an environmental factor. And then our polar bears. Our polar bears will often den on land, or they spend some of their time on land, but then they will go out to hunt on the sea ice. And so the problem is that as that sea ice retreats, or if it moves rapidly away from land, then they can have to swim very long distances to find those seals. And also as our seal populations decline and our walrus populations decline, then it's going to be more difficult for them to do that. So really we're seeing loss of that sea ice as a loss of habitat, of just sort of an area for this animal, but also just in terms of changing the rest of the ecosystem and how it's structured itself. Okay, so we'll see how our polar bears do as well. And lastly, something we don't often think about are whales. We have a couple of species that are really special and unique to the Arctic. Does anyone know what these ones are called? beluga whales, so our white whales there, and obviously you can tell they're adapted to an ice environment, they're white. But also, along with them, and also, what are the ones on the top right? Narwhals. They don't have dorsal fins, they don't have fins on their backs, and that's a factor of them living under sea ice, okay? And they also have pretty advanced echolocators as well. And so these are very specifically adapted to Arctic environments and sea ice environments. And the question is how they're going to cope when there's more competition potentially arriving from the Arctic and Pacific from other species, okay? So the question is there. And then it's worth pointing out that we think of ourselves as entirely removed from ecosystems often. And for a lot of the indigenous peoples of the Arctic, they really are very much still dependent on sort of their food sources. So things like seals, caribou, walrus, things that use the Arctic sea ice. And as that sea ice disappears, then their traditional way of life, their traditional sort of way they use resources and obtain resources is also going to change. And they are seeing some very dramatic alterations in their environment as well. So it's not just them. So I'm going to be done a little bit earlier today, but there's plenty of things for you to read. Okay, I'll see you on Friday.